Hello guys. Now we will discuss the very famous example of the MATLAB MathWorks, which is used to simulate the fault-tolerant control system. So this is the model a fault-tolerant fuel control system. So modeling of a fault-tolerant fuel control system. This is the title of this lecture. This example shows how to combine stateflow with Simulink to efficiently model hybrid systems. The type of modeling is particularly useful for systems that have numerous possible operational modes based on discrete events. Traditional signal flow is handled in Simulink while changes in control configuration are implemented in stateflow. So this is a stateflow based diagram in which there will be different scenarios and different states will be followed by the model. The model described below represents a fuel control system for a gasoline engine. So this is a gasoline engine. This is for the gasoline engine. The system is highly robust in that the individual sensor failures are detected and the control system is dynamically reconfigured for uninterrupted operation. Okay, analysis and physics. Physical and empirical relationships form the basis for the throttle and intake manifold dynamics of this model. So this is the mathematical modeling regarding how the model is made. These are the basically equations, and the air fuel is computed by dividing the air mass flow rate pumped from the intake manifold by the fuel mass flow rate injected at the valves. So this is known as the AFR ratio. This is very important in the combustion systems. We need to maintain a proper air fuel ratio for optimum combustion efficiency. So this is according to the stoichiometric ratio, the stoichiometric equation. These are mentioned in my research papers. You can download these from the internet. The ideal stoichiometric mixture ratio provides a good compromise between powerful fuel economy and emissions. Okay, between power, fuel economy and emissions. So these three things are very important. So emissions for proper combustion, if you give proper air fuel ratio, then you will have less unburned carbon. So this will be beneficial for the environment too. Okay, if there is high air in the ratio in the system, then it will be termed as the lean mixture, and if there is high fuel in the mixture, it will be termed as the thick mixture, and the air fuel ratio will become lesser than the stoichiometric ratio. So both lean and rich mixtures are not good for the combustion. The best mixture will be the ideal or stoichiometric combustion system, in which the air fuel ratio is optimum according to this stoichiometric ratio. So the target air fuel ratio for this system is 14.6. so this is for the gasoline, and this is different for different fuels. Like if you use different fuel, you will be having the AFR according to the stoichiometric chemical equation of that fuel. For the gasoline, it becomes 14.6, and this has been mentioned in my research papers. Okay, and typically a sensor determines the amount of the residual oxygen present in the exhaust gas oxygen. So there will be some oxygen which will be detected in the exhaust gas, and it will be sensed by the ego sensor, and this gives a good indication of the mixture ratio and provides a feedback measurement for the closed loop control. And this based on the feedback from this sensor, we can judge that either our mixture was stoichiometric or not. So this is the sensor for the stoichiometric ratio, AFR ratio. If the sensor indicates a high oxygen level, the control law increases the fuel rate. So if it indicates high oxygen means there is much air, then the control law will increase the fuel rate, it will increase the fuel. When the sensor detects a fuel rich mixture, then corresponding to a very low level of the oxygen, if the oxygen is low, it means the mixture is greater and air is less, then the controller will decrease the fuel rate. So this is the control implemented in the model. And the equations of the model are missing in this page, but these are mentioned in another page. And these are basically taken from a very famous research paper of the Hendrick, which I will show you that the base reference of the whole model. This is a very famous, very well known and very accurate model of the gasoline air fuel ratio of the gasoline engine. And this is the other page at which the equations are mentioned of the model. Like these are the equations, these are based on the empirical results, the experimental results. The experiments were performed, and this project was funded by the Ford company. Like here, this is the main thing. The model is based on the published results by Crossley and Cook 1991. So this is a very accurate model, and it's being used by the MATLAB itself, and you can use it for your further research, working further controller design, and you can check their working on this model. Okay, it describes the simulation of a four-cylinder spark ignition internal combustion engine. The Crossley and Cook work also shows how a simulation based on this model was validated against a dynamometer test data. So it was validated also, and I show you the references for the model, because this is because some researchers, they say that the what is the model of the working. So this is the model. Crossley and Cook IEEE Conference Control 91. So this is the main reference. The other references are mentioned here, like Ford company reference is mentioned here, Hendrix, Cook, and this is Moscow. So these are very famous engine models which are being utilized to make this very beautiful model, and you can work on this. So these are the equations, mathematical modeling, and these are empiricals. These are also basically, these you can say that these are derived from the generic equations. If we put certain parameter for the generic parameters, then you will get these equations ultimately. So now coming back to the modeling. So the model was based on the equations and papers which I showed you, and it was experimentally verified according to this MATLAB works and the published papers. Okay, now I come to the model. So this, you can see that there are basically four sensors which are considered here, very important sensors. These are throttle angle sensor. This throttle angle is basically the air throttle actuator angle, okay, from which the air is coming. And the other one is the engine speed sensor, and third one is the ego sensor at the exhaust which is installed, and finally fourth one is the map sensor. This is the pressure sensor of the air which is being fed to the air fuel ratio. So this is the pressure sensor of the air suction manifold. So these are the four sensors, okay, and these are basically, this is the convert block which is converting their data types, and this goes to the fuel rate control, at which the fuel rate control algorithm is implemented using state flow, and the fuel rate is coming out which is in gram per second, and which is going to the plant. So this is our plant, which is the engine gas dynamics. So this is our plant in which we get fuel from here. And throttle angle, this throttle angle is coming from this block. This is the throttle angle of the your throttle actuator, and this is the engine speed which is being fed here, at which the engine is running. Okay, so this is the speed sensor, and this is throttle angle sensor, and this is your fuel which is coming, which is being calculated again. Now what is the output of the block? Its output is the oxygen content in the exhaust, the map sensor in the manifold, the pressure sensor in the manifold, and finally the air fuel ratio, okay, which we have to maintain at 14.6. now this is the simple simple fuel control system. We have to make it fault tolerant. Fault tolerant means there are four sensors here basically, and if a fault arises in any one sensor, the system should be able to tolerate that fault, and it should continue working. It should not shut down or stop. It should not shut down. I would use the word shut down. So how we simulate the fault? So this is how we simulate the fault. We have a fault injection unit. Okay, we have a fault injection unit. You can see here the fault injection unit, at which there is throttle angle, normal. This is the slider switch. If you push it here, then it becomes fail. Okay, this is the binary fault we have implemented here. So it's binary fault which is implemented here, and there are two speeds at which the model is working. One is 300 rpm and the other is 700 rpm. So this model can also work at higher speeds like 1000 rpm, 1500 rpm, but it is shown, the work here is shown for the 300 and 700 rpm. So mostly the work is being done at the 300 rpm because of the standard speed of the MATLAB model. Otherwise this model can also work on the 100 and as well as higher rpm. I have tested it and it works successfully. And this is the fuel gauge, and this is the air fuel ratio, which should be between 12 to 16. In case it should work on 14.6, and if a fault arises, it should not go out of this band 12 to 16. Okay, and these are the below are the dashboards for the parameters. I will show you its simulation. Okay, so how, when you press this, when you make it fail, what will happen when you make it fail? Throttle angle. Here we have a throttle switch, so basically this button is controlling that switch. So if it is 1, okay, it's normal. This is a selector switch. 1 means the normal value is coming. Okay, so this normal value is coming through. This is a simple, you can say it's sort of like the control line and multiplex mux, you can say just like a multiplexing sort of multiplexer. So if you make it 1, the throttle value will be passing, the engine will be working normally. So this is basically this is working normally. So if you make it 0 here, if you make it 0, then what will happen, this false will become enable and the output will be connected to here. Okay, now 0 will go through. So if you inject the fault, then instead of the throttle value, 0 will be coming here. Like this clearly means that the throttle angle is now faulty. It's giving 0. 0 means fail low. Normally we have two big extremes, fail safe low and fail safe high. Here we have modeled it as fail safe low, fail safe low. So for the second thing, for the second engine speed sensor, similarly the normal speed, which is 300 rpm, it is being passed when it is 1, and if we make it 0 through this slider switch, then 0 gets to the further at the sensor's value, and this is simulated as fault in the engine speed switch. The third one is the ego sensor. For the ego sensor, if 1 is pressed, the ego value is going, and if you press it 0, then 12 will go through. Why 12? 12 here, this is the upper scale value, like 12 volts, because 0, if we give it 0, 0 actually comes in the operating range of the ego sensor. That's why 0 is not used, because it's in the range of the sensor working. So we have given here, the model MATLAB has given here the 12. This we can say that the fail high condition. This is the fail high condition at which 12 value is passed. The value of the ego sensor is normally from 0 to 1. The operating range of the ego sensor is from 0 to 1 volt. So 12 is the fail high. You can say it's 12 volt means the sensor is fail high. So failure state is going forward. And lastly is the pressure sensor. So if the pressure is its value is also if it is 1 means normal value is going in the pressure value, and if we press it to 0, okay, then it means the 0 value is going into the pressure, which is definitely a faulty state, 0 for the pressure sensor. So this is how the fault injection unit and fault injection is modeled in the MATLAB. So that you can follow the same process in other systems like emergency vehicles, your electric vehicles, or emergency braking system, electric vehicles, and similarly your quadcopters. You can similarly make the fault injection unit, as well as your fault injection unit and fault traveling. You can similarly make your selector switches in that model, and you can similarly make the models for the actuators. This is for the sensors here. You can make for the actuators here as well. Like this is the fuel which is coming from the fuel actuator, so you can make here model as a fuel actuator fault. Okay, further this is explaining further the fuel rate control system. Like here we have the sensors, we getting the sensors value here, either normal value or the faulty value. Okay, now comes the sensors fuel rate control block. So this is the block for the fuel rate control system, in which the sensors value are coming into this control logic, and these are the inputs of the sensory inputs, 4 inputs of the sensors, and these are the 3 outputs which are coming from this: the ESO oxygen value, oxygen normal state, and fuel mode. Okay, Then comes the air fuel calculation block, from which the air is being calculated, and finally the fuel rate is being calculated in this block. So you can further go in depth, and these are all explained in my papers. You can see those things in my papers as well. And this is the control logic, like oxygen pressure, throttle speed, and for example, so this is the state flow, basically different states. If there is no fault, then it is going here none, so it will fail none, and the system will be working normally. And if there is one fault in one sensor, then it will go to the one state, okay, and in one state. And if you put fault in two sensors, it will go into 2, 3 or 4 faults, and this will be the multi-sensor fault, the fault in simultaneous faults in more than one sensor. So in that case, the engine will shut down. The model is programmed to tolerate only one fault at a time. So this is the limitation of the model, that it can handle only one fault at a time. So this is the fueling mode. You can see that the model, when the model is running, so it's in the first is the warm-up period. It's in the every engine there is certain warm-up period. After that warm-up period comes the normal state, okay, and if the fault comes, it goes to the single failure, and if you remove the fault, it goes back to the normal state. But if you put again fault here, in case of multi-fault, then it will shut down. Like if you further make it faulty, then faulty.multi, it will shut down, okay. Similarly, if you overspeed it, like from 300 to 700 rpm, it will again shut down, go to the shutdown, okay. So this is how the block is implemented here, okay. And these are the sensors. If it's working normal, okay, it will be producing the value. However, if the fault comes in the sensor, then it goes to the fail state, and from the fail state there comes the working of the active fault tolerant control, which is this is a sort of active fault tolerant control in which the estimated value will come out. So this is the observer, you can say this is the observer of the model, and this will be working based on the lookup table. So this model is basically built based on the lookup table. And how it is retrieving the value of lookup table? So when this pressure sensor becomes faulty, this lookup table will produce its estimated value of the pressure based on the other active healthy sensors. So the other healthy sensors, the model will produce the estimated output, and that estimated output, you can see that map estimate is a function of speed and throttle. So from these two sensors, it will generate the estimated value, and this estimated value will be fed to the engine controller in case of fault, in case of single sensor fault like this fault. So this is the lookup table, which is made using the experimental data which I mentioned earlier by the dynamometer testing model. And this is the airflow calculation block, and you can go through it to understand how it's working. So this is basically implemented using these equations, and further these details you can find in the papers of the Hendrik as well as my papers also. You can find these details. Then comes the so this is the equation here, which is implemented in this here, okay. So this is how the whole systems work, and this is how the fault tolerant fuel control system is implemented here. The first graph is shows for the normal operation. This is the normal operation, and this below graph shows the fault. There is fault in the throttle sensor, but in the fault after the fault, the system becomes normal, it does not shut down. So this is the fault tolerance which is implemented for these four sensors in the model, and this is the air fuel ratio. This is the normal air fuel ratio, okay. And if you put a fault in the throttle sensor, it goes faulty, but it comes back and degrades a little. So this is the concept of active fault tolerant control. You can find in the other my video of the advanced control system, fault tolerant control system. You can find the working concepts of the active fault tolerant control, passive and hybrid. So this is for the active. We have the stability maintained but with little degradation, okay. Similarly for the other sensors, and this is, you can see that the system is able to tolerate fault. Now I run its simulation like this is the scope, which is for the 8 second. I have made it 8 second, but I can make it 15 second to observe its behavior for greater time. So let's make it first 15 second. Time span is 15. Okay, so we run it. I make it normal all sensors, so we run it for the 15 seconds and it's run. You can see the normal behavior. This is the normal behavior. You can also make changes in its displays. You can log its data and make Excel sheet as well. And style, if we change its style, like make it white. Okay, and we make it red. Okay, so this is for the 15 second we have it. I run it again. You can also run from here. Now I introduce a fault in the throttle sensor. Okay, now you can see that the fault is implemented after 5 seconds. Actually the fault is implemented at the very first state, but there is the delay, some delay, which is delay for the warm-up period, the engine warm-up period, which is in every practical engine we have this warm-up period like this. You can see that this warm-up period. So due to this warm-up period we have this delay. Okay, I run it again, and since there is fault in one sensor, you can see that here it is 1. Okay, I can also make it run perpetually, like if I put here infinity, then it will be continually running, and you can see here that it's one fault. Okay, if I remove the fault here, then it comes again to the none. But if I put the fault again here, then you can see that it comes into the faulty sphere. So if I put another fault simultaneously, the engine is shut down. In that case, this is a shutdown. Okay, this is a shutdown. This is a shutdown. Okay, so we need to have one fault at a time. So okay, let's make again 15, and now put the fault in engine speed sensor and run it. Okay, again it's fine, it's working. Okay, and it's on the lower side 11 point something, 11.6. okay, then put the fault in ego sensor. Okay, and now put a fault in map sensor. Okay, now if we want another simulation of a fuel actuator, like this is for the sensor line. Let's make for the fuel actuator. If I copy it from here, fuel actuator. Okay, you can modify its format. You can increase its format like Okay, so here you can have this fuel is going into this. You can apply a fuel actuator here. And if the fault comes here, then the fuel is cut here. Okay, so I again copy here like this. Okay, and then I again make a switch here. Okay, now I name it as actuator switch. Okay, and I have to define it in the workspace, and I define it as 1, create it and make it as 1, and here on this side on the dashboard I give it here name. It should rotate here. So if I press it here, I make select it. Okay, now this is being controlled here. So this is how I have implemented here the fuel actuator fault. You can model it as like these are basically ignition coils, and if the fuel actuator is it's the injector ports. These are the injector ports from the fuel is going into the engine gas air engine manifold at which the air fuel combustion is being done. So now I run it, make it faulty, and you can see that. Let's make it infinity and observe on the real time. So you can also check it like this. Now its value, you can check its value, it's 0 is coming, and if we make it 1, okay, it's 1. Yes, it's working. And we can also it's the okay, actuator, we make it so this is the actuator we selected. Okay, now we apply it here, and now we check it here. Yes, it's working fine. Okay, and similarly here, if I put it, if I check the value of the fuel, it's 0.9 to its normal value, and it's 0. Yes, it's working. So this is how we can simulate the our system. So if I check its response, like make it 15 and put a fault here and run this your engine, so you can see that the fuel is 0, and the fuel is 0, and your air fuel ratio, since air over fuel, so this is in the denominator, it will become a very high number. So here we can see that it shoots a lot, and this is according to the air over fuel ratio. Okay, so it becomes very large, and the system, this is here is basically it is in shutdown, and this is oscillating because of the air throttle input which is being fed from here, and its AFR is being calculated here. So from here we see that this is the ratio, and if I put here as 0, so this becomes a very large number. So this is how the fault tolerant fuel control system is working, and its estimation in this example is being done from the lookup tables, and you can further do for future research by making more advanced estimators for these four sensors, and by the combination of hardware and hardware redundancy. This is basically the virtual sensor, the observer based sensor. This is the virtual redundancy, and if you apply a practical sensor, another sensor in parallel to that, you have a hardware redundancy. So these are the various fault tolerant control strategies which are explained a lot in my other lectures of the fault tolerant control, as well as in my research papers. You can find them, and you can do more search and on this system, as well as following the same procedure on the other systems. Thank you very much for listening.